we will only care about Stirling numbers of the second kind in this class. And if I say we care about the Stirling numbers of the second kind, that implies the existence that there are Stirling numbers of the first kind. Only, again, we're not going to care about those. We're not going to really study those. The more practical set of numbers is the Stirling numbers of the second time. And so if I just say the word Stirling number, I'm talking about Stirling numbers of the second kind. The only reason I bring this up is because if you get on Wikipedia later and you search Stirling number, it's going to come up with 2 different types, and I don't want you to be confused because we're not dealing with the first type. In fact, if you were to Google search Stirling number, the first thing that comes up from MIT Mathematics is Stirling numbers of the second kind, and Wolfram Math World Stirling numbers of the second kind. So you can tell that it's the more popular version of the Stirling numbers, right? Okay. So we're going to use a capital S with 2 subscripts to represent Stirling numbers. And a Stirling number is the number of distinct partitions of a set where the size of the set is size n. That's the first number in the subscript. And we're going to partition the set into k blocks. And so that's the second number that appears in the subscript, is the number of blocks. A block, I should have put a definition for block, but a block is a disjoint subset. Specifically, a disjoint non-empty subset. So if I partition your set into blocks, then every block has at least one element, and they don't share elements. They're disjoint from one another. In other words, SNK is the number of ways to sort n distinct balls into k indistinguishable buckets. So you can tell the balls apart, but you can't tell the buckets apart. Also, the Bell number is the number of all partitions. So to get the Bell number for a set of size n, you add up all of the Stirling numbers, because you could have 1 block or 2 blocks or 3 blocks and so on up to k different blocks. All the way up to n different blocks. So you add up all those Stirling numbers and you get the Bell number. Okay, so how many partitions of 2 blocks does the set 1, 2, 3, 4 have? Well, in this case, my set has a size of 4, and I'm going to have 2 blocks. And so I'm talking about the Stirling number S with the subscript 4, 2. But practically, if I was going to count these, I could have 1, 2, 3, 4 with a partition like that. Or I could have 1, 2, 3, 4 with a partition here. Or I could have 1, 2, 3, 4 with a partition here. Right? That's 2 different blocks here and here. Are there any other ways to partition this set into 2 different blocks?
Can you change the order of the numbers?
Yeah, I can change the order. So instead, I could say, let's start like 2, 3, 4, 1. And now I can partition the 2 by itself. We haven't done that yet. 2, 3, 4, 1. And I could partition the 2 and the 3 by themselves. We haven't done that yet. You could say 2, 3, 4, 1. And I could partition the 1 by itself. But we already did that, actually. So we've exhausted that permutation. There's probably a better way to count this than what I'm doing now, but I'm just hoping it's a relatively small number of permutations, or a small number of partitions.
Can 0 in one section and 4 in the other section?
No,
Okay.
not for this type of counting problem, because we want our blocks to be non-empty.
Oh, okay.
Yeah. Good question, though. So I don't know. Maybe a smarter way of counting this would be like, what would a partition look like if you could only have 2 and 2, right? Like I could have 1 and 2, or 1 and 3, 2 and 4, or 1 and 4, 2 and 3. So I've got the ones. What about, oh, I've already got 2 and 3 together. Do I have 2 and 4 together? Okay, I do have 2 and 4 together. And I have 3 and 4 together, 3 and 1, 3. Okay, that's all the ways I can do 2 and 2. The other option is 1 and 3. Aha. And that's it. So I think this Stirling number is 7. I think that's the answer to the question. How many partitions of 2 blocks does the set 1, 2, 3, 4 have? And notice I don't really care about the order of the elements, but I do care which block they're in. The elements of the set are distinct from one another, but the blocks themselves are indistinguishable. And I don't care about the order of the elements within each block. Questions? Let's do another example and see if we can think about this again. How many partitions does the set 1, 2, 3, 4 have? Might sound like the same thing, but earlier we were only counting partitions with 2 blocks, right? And so I know that this has 7 partitions of 2 blocks. But how many partitions of 1 block are there? 1, right? How many partitions of 4 blocks are there? Right? If I was going to put each element in its own block. And then, okay, the more interesting question now is how many partitions of 3 blocks exist? So we've got elements 1, 2, 3, and 4. And if I was going to put down 3 different blocks, I could have only 1 block that has 2 elements together. And then the other elements would have to be in singleton blocks. Like, that's a way to do it. I could also make that a way to do it. I could make that a way to do it, so that 3 and 4 are together. Now if I grouped 1 and 2, 2 and 3, 3 and 4, I could group 1 and 3 together, whereas 2 and 4 are not. I could group 1 and 4 together, where 2 and 3 are not together. So 1 and 2, 1 and 3, 1 and 4, 2 and 3, I could group 2 and 4 together, whereas 1 and 3 are not together. And have I grouped 3 and 4? Yeah, I grouped 3 and 4 already. So I think there are how many partitions of 3 blocks? 6. So the answer to my overall question, how many partitions does the set have? This is a question that's asking for the Bell number of a set with size 4. And the 4th Bell number is going to be 7 plus 1 plus 1 plus 6, which is 15. Okay, questions? No? How many partitions, I think this is my last, okay, this is my last question here. How many partitions of 2 blocks does the set 1, 2, 3, 4, 5 have? And again, we got to be a little bit careful about doing this because this is going to be a long problem, I think. And the goal is we're going to first do the partitions with 2 blocks where I have a singleton. And so each number gets to take turns being a singleton. Okay. And then we have to move on to partitions where we have 2 and 3 as the size of my blocks. And so the ways that I can get this group of 2 could be 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. And the other elements here are predetermined, right? The remaining 3 elements after I choose a group of 2. So altogether, the number of 2 blocks that a set with size 5 has is the Stirling number S 5, 2. And the answer is 15. Okay, so we're clear about what the Stirling numbers are counting, right? All right. So we have a recurrence relation for Stirling numbers. And I mean, you can see how one Stirling number relates to 2 other Stirling numbers with slightly smaller sets and numbers of blocks and whatnot. We say that S in comma K is equal to the Stirling number S in minus 1 comma K minus 1. So a smaller set partitioned into fewer blocks plus K times the Stirling number S in minus 1 comma K. So a smaller set partitioned in the same number of blocks, also times K. So let's reason about this using our combinatoric skills. We're going to say, suppose A is an element of set A, and set A has a size n. On the left side of this equation, the Stirling number S in sub k is the number of partitions of A with k blocks. On the right side, we've got 2 parts. We've got the first Stirling number plus k times the second Stirling number. So let's talk about the first Stirling number. The S in minus 1, k minus 1 counts the number of partitions of A in which A forms a singleton block. Okay, so think about that for a second. If I take the element A away from my set, now I only have n minus 1 elements. And also, if I tell you that A forms its own block and it doesn't let any other elements be part of its block, well, then I also have k minus 1 blocks left to partition the other n minus 1 elements. So if I go ahead and make the choice that A is going to be a singleton block, then the number of ways I can partition the set capital A is this. It's just like a restricted way to partition it, okay? The other part of the right side of this equation, k times everything else, n minus 1 comma k, counts the number of partitions of A where A belongs to a block of size greater than or equal to 2. That also might take a moment to digest really quick. What you're going to do is you're going to come up with a partition of the set capital A excluding lowercase a, in which you would have n minus 1 elements, and you're going to partition it into k blocks. After you've done that, you still haven't placed your little lowercase a element yet. And how many choices do you have for placing where the a goes? It has to go into one of k partitions. So the multiplying by k is telling you about how many choices you have for placing the little lowercase a after you make this number of partitions with the other n minus 1 elements. Okay? And by partitioning the other n minus 1 elements first and then putting the a in later, you've ensured that A belongs to a block of size greater than or equal to 2. Because the partitions were non-empty before you put A in one of them. Okay, so we have counted in two ways. So we say the identity follows by the rule of counting in two ways. In other words, the left side of this identity, the left side of this equation is counting the number of partitions of A with k blocks, and the right side of this equation is doing the same thing. It's just doing it in a different way, right? A slightly more complicated way. Because it's an either-or situation. Either the element A is a singleton block, or the element A belongs to a block of size greater than or equal to 2. So that covers all your bases, and we're counting in two ways. And so we get this neat recurrence relation. And what the recurrence relation does for us is it allows us to write a Stirling matrix. And in a Stirling matrix, we're going to have n's and k's, where let's say n is 0, 1, 2, 3, 4, 5, 6, 7. And k gets to be 0, 1, 2, 3, 4, 5, 6, 7. I should print myself like a table instead of having to draw my table by hand, because that's not enough room at all. I really should have just come up with this. My typesetting instead of by pen. Okay, now let's try it. If I have a set of size 0, and I wonder how many ways I can partition this with 0 blocks. Actually, it doesn't even make sense to start with 0, does it? We'll skip the 0 part because that's kind of, you can't have a partition with 0 blocks. So here we go. Trying again. If I have a partition of 1 block, there's only one way to do that. It doesn't matter what the size of my set is. There's only one way I can partition a set into 1 block, and it's the block with all the elements in it. Likewise, if n is equal to k, the size of my set is equal to the number of blocks I'm using in my partition, there's only one way I can possibly do that. So on the diagonal of this matrix, where I've got 3 and 3, and 4 and 4, and 5 and 5, 6 and 6, and 7 and 7, there's only one way to partition a set of size 7 into 7 blocks. Right? Okay. What else? I know from my recurrence relation that Sn comma k is equal to Sn minus 1, k minus 1 plus k times Sn minus 1 k. So that means if I want this entry right here, 3 comma 2, I would have to add 2 comma 1 plus 2 times 2 comma 2. So this number should be a 1 plus 2 times 1. It should be a 3. Okay. Just below the 3, where I have to add 1 plus 2 times 3, 7. 1 plus 2 times 3 is 7. Okay. To the right of the 7, where I've got 3 plus 3 times 1, that's going to be a 6. Okay, below the 7, this has to be a 1 plus 2 times 7, 15. Below the 6, this has to be a 7 plus 3 times 6, 25. And below this 1, to the right of the 25, we have to have 6 plus 4 times 1, 10. Below the 15, 31. Below the 25,
81.
I heard the correct answer. Got it. Okay, because 15 plus 3 times 25. Okay, below the 10, we get
One bit. 60.
okay, and to the right of the 65, we should have 15. Below the 31, below the 90, below the 65, below the 15,
You're just getting over it too quick.
because it's 65 plus 5 times 15. So it's 65 plus 75, which is 60 plus 80, which is 140. And then 15 plus 6 times 1 is 21.
I got it.
All of the stuff above here is 0, by the way, right? Because I can't partition a set of size 3 into 4 blocks, right? Because blocks should be non-empty disjoint subsets. And so all that stuff above the diagonal is zeros, yeah, that's it. So you can use that recurrence relation to fill in the Stirling matrix. And we can go back and look at some of these questions we answered at the beginning of class in a little bit more of an illustrative way and ask ourselves, did we get the answer right? You know, if I have 4 comma 2, is the answer supposed to be 7? There's my 7, 4 comma 2. All right. When we did 4 comma 3, we got the answer 6. Okay, we got that right too. When we did 5 comma 2, I remember getting the 15 for 5 comma 2. So we got those. How would I calculate a Bell number?
Add up all the numbers in the rows.
Yeah, exactly. If I wanted the 6th Bell number, I would just need to add up the horizontal here. That would give me the total number of ways I can partition a set with 6 elements by adding up those numbers. Okay, questions? The one thing I'll say is the one thing I'll say is like we had I forgot what we called it, but we had a matrix like this for the binomial coefficients, where like the n choose k was the row choose columns, like the rows were n's and the columns were k's, and we had n choose k in each thing. And there was also a recurrence relation for the binomial coefficients. It was different. It was not the same recurrence relation, but it was slightly different. And in a way that was like optional to make that matrix, like it was cool to have the Pascal matrix, but using the Pascal recurrence. That was kind of neat, but you didn't have to because binomial coefficients had that closed formula in terms of factorials. Like n choose k is n factorial divided by k factorial divided by n minus k factorial. But the thing about Stirling numbers is that there's not a very neat closed formula. There is a closed formula, but it involves a summand. It involves adding up a finite but large number of terms, right? And so in a way, if you were solving problems by hand, writing down the Stirling matrix is actually the fastest way to calculate Stirling numbers. It's way faster than trying to draw the partitions by yourself, right? You wouldn't want to do that for 350 partitions. Okay. The following recurrence relation holds for Bell numbers. And once again, if you were asked to prove this, you're going to prove it using the rule of counting in 2 ways, where the left side of the equation is counting something, and the right side of the equation is counting the same thing in a slightly different way. So notice the definition of the Bell number would say that Bell n plus 1 counts the total number of ways to partition a set A with size n plus 1. And then we are going to do something really similar to what we did before. We're going to choose one element in the set capital A and name it A, little lowercase a. You can name it whatever you like, but we'll use lowercase a. So what's happening on the right side? The right side of the equation is obviously a sum where each term is counting the number of partitions where A belongs to a block of size. Ooh, what size is the block that A belongs to? N plus 1 minus k. All right, so let's think about this. If my element belongs to a block of size n plus 1 minus k, and my set has size n plus 1, how many other elements don't belong to the same block? K, right? So K elements belong to a different block. Not A's block. And for these K other elements, there would be bell of K, number of ways to partition them. So that explains part of our sum and over here. That's the number of ways I can partition K elements. The n choose K part, that binomial coefficient, is telling me the number of different ways I can choose K elements out of n elements to not belong to A's block. Notice the set capital A has a size of n plus 1, but this is only n choose K, not n plus 1 choose K, because A, our little element lowercase a, is going to be in A's block. There's no way to avoid that. So there's n other elements, and from those n other elements, I've got to choose K of them to not belong to A's block. And if it doesn't belong to A's block, then there's bell of K ways to partition those. And so I multiplied to get the total number of ways that I can write a partition of the set A where my element lowercase a belongs to a block of size n plus 1 minus k. And when I add all of these up, where k gets to be equal to 0, meaning that every element belongs to A's block, all the way up to k equals n, where A is in a singleton block and all in other elements don't belong to K's block. Adding up all of those possibilities is going to give me the left side, which is the total number of ways to partition the set. So, counting in two ways. Okay. And so then you say ... therefore counting in two ways blah, blah, blah. Since the left side and the right side are counting the same number in two different ways, that has to be true. So now we have a recurrence relation for Bell numbers. Great. Of course, it's not a very nice recurrence relation. Like anytime a sum appears, like that's not very good. But it's something you could do. Next. Suppose we have n distinct balls in r distinct buckets. How many ways can we arbitrarily put the balls into the buckets? I'll let you guys answer this one. It's an easier question. Distinct means I can tell them apart, like the balls are all different colors. The buckets are all different colors.
Does there have to be at least one ball in one of the buckets?
Nope. You can have an empty bucket if you want to. You can put all the balls in one bucket.
Doesn't matter which bucket. Right.
Yes, the buckets are distinct. Okay. I guarantee you're probably overthinking this problem.
be like N choose R?
So let's think. When I have the red ball in my hand and I'm deciding which bucket to place the red ball in, how many choices do I have?
4.
4 choices. Okay, so I place the red ball. Then I move on to the orange ball. I have the orange ball in my hand. How many places can I place the orange ball? 4. And then whenever I have the yellow ball in my hand, how many options do I have? 4. When I have the green ball, there's 4. So is there any way that I can succinctly write this formula?
That would be n to the r power. No, r to the n power.
R to the n power. Nice. Yeah, because for each ball, we have r choices. And since these are independent of each other, I'm allowed to have empty buckets. I'm allowed to put all the balls in one bucket. They're independent choices we can multiply through by the number of choices.
That is an easier question.
Suppose we have n indistinguishable balls. So they're all the same color now. The balls, you can't tell them apart. And r distinct buckets. So you can tell the buckets apart. How many ways can we put the balls into buckets so that each bucket gets at most one ball? So here are our, here you can think about it. I won't interrupt you.
Yeah, at most one ball. Oh wait, oh, at most? I misread that.
My picture is not very good since there's at most, right? If it's going to be at most one ball, then
Then it would go bigger.
I need more buckets than balls, don't I?
So r must be greater than n.
You're right. R really needs to be.
Greater than or equal to n.
Mm-hmm. Actually, be easier for me to delete balls than it would be for add buckets. Okay, so that's the picture. There's more buckets than balls.
Okay. Is it just n factorial?
R choose n.
Oh, he said r choose n, so I think it would be r choose n. No, it's
Is
r
it
factorial.
R factorial over R minus N factorial?
I think this is R choose N.
I'm just thinking this is like if there's a binary string, then you'd have the buckets and how many bits you would have, and the balls would be how many are one.
At most one ball means that a bucket either has one ball or none. So we are choosing which bucket gets a ball, which buckets get a ball, and how many buckets can we choose? We can only choose n buckets. So this is a matter of 6 choose 3. We choose which 3 buckets will get a ball out of the 6 buckets. So in other words, 6 choose 3, R choose n. Okay. Let's try another one. Suppose we have n distinct balls and r indistinguishable buckets. How many ways can we put the balls into buckets so that each bucket gets at least one ball? The buckets are boring this time. The buckets are indistinguishable. And because we need at least one ball per bucket, that must mean I have more balls than buckets.
How many ways can we choose two numbers from this list?
Yeah.
That's why it said that way. So you can choose these two. You can choose
So
these
just-
two. You
okay.
can choose these two.
I got you.
This one.
Choose. So it would be, and choose R then? Question mark?
No, but we're putting blocks all around the list. So it'd be like, I think this would be the starting number.
This is,
Because we're putting a list of numbers
I was
into
thinking
blocks.
you pick at least. Right. Yeah.
N choose R would be the number of ways you could choose 4 out of these 6 balls.
It's at least one ball, not at most one ball per each bucket, so that's not the same.
Yeah, it wouldn't be the same.
Stirling number. Because we're putting balls in buckets, but it matters which ones are in which bucket. So it's string number, is it like the N or?
You're right. So the answer to this is the Stirling number. Because I have a set of size n and I want to partition it into R blocks. Here's my set of size n, and partitioning this means I put them in disjoint, non-empty subsets. I put them into blocks. So the buckets are the blocks, the balls are the elements of my set. So this is the definition of Stirling number, and you would only be able to calculate this with the recurrence relation and everything we talked about. So this is just the kind of a definition thing. Okay. Suppose we have n distinct balls and r distinct buckets. How many ways can we put the balls into the buckets so that each bucket gets at least one ball? Yeah, we have distinct balls and buckets, huh?
This you would assume that N and R are over.
Each,
Yeah.
this needs to be at
They
least
have to
one.
be and it's greater and equal to R.
Would it be the bell number?
The bell number is the total number of ways to partition a set, and so if we were going to include the bell number, you would need to like allow a variable number of buckets. Right? But we're saying this has to be R buckets. It's not any number of buckets.
This doesn't have any factorials in it, does it?
It could. I didn't say it couldn't.
Is it the Stirling number of NR times R factorial?
Yeah, that is.
Yeah, sure.
Okay, so if I take R factorial times the Stirling number NR, the reason why this is the case is because, remember, when it didn't matter what the buckets were, it was just the Stirling number, the ways to partition this set into these blocks. The R factorial shows up because we're talking about a permutation now of these buckets. Like it matters which bucket the balls went into and how many different ways can you reorder the buckets. R factorial different ways. That feels right. Okay. Suppose we have n distinct balls and r indistinguishable buckets. Oh, sorry. The balls are distinct, the buckets are indistinguishable. How many ways can we arbitrarily put the balls into the buckets? And this time there's no requirements, right? Like you can have empty buckets if you want. You don't have to have empty buckets. You can put more than one ball in each bucket.
R to the n power?
Yeah.
It's not r to the n power. I think this one's a really tough one, actually. Let me tell you what I think it is. I think what you would need is you would need to say, I'm allowed to have empty buckets. And so if I took like a Stirling number where I took all the balls and I put them into K buckets, that would describe part of the situation. I want to say this is the answer. The reason I think this is the answer is because I could put everything into one bucket, right? I could take all of the balls and put them into one bucket. So when k is equal to 1, this is the number of ways I can partition a set of size n with one block. Of course, the number is 1, but you know, Now imagine k is 2. Okay, so I'm taking all of these balls and I place them into 2 of the buckets. Doesn't matter which 2 because the buckets are indistinguishable. But since I'm allowed to have empty buckets, I'm allowed to leave the rest of them empty. And now I've just put all the balls into 2 buckets in as many ways as possible. And so I'm adding another Stirling number to that where it's SN2. And then you go with k equals 3, k equals 4, k equals 5, all the way up to R because I only have R buckets. And so whenever I have the Stirling number S in R, that's using all of the buckets where none of the buckets are empty. And the number of ways of doing that. So it's not just the Stirling number, it's the sum of all of the Stirling numbers where k goes from 1 to R. This is different from the Bell number unless you had just as many buckets as balls. But if R is equal to n, this would be the Bell number. It's probably less than the Bell number unless you have as many buckets as balls. Okay. That's a tough one. Suppose we have n distinct balls and r indistinguishable buckets. It's a good format for a counting problem. How many ways can we put the balls into the buckets so that each bucket gets at most 1 ball? So if each bucket gets at most 1 ball, that means I need more balls than buckets. Sorry, more buckets than balls, right? I've got more buckets than balls this time. The buckets all look the same, but the balls look different.
Is it just n ways to do it? However many balls you have?
Why do you think it's n?
Because all the buckets are the same. So it doesn't, all of the balls will go into a bucket. They'll all be in their own separate buckets. All the buckets are the same, so it doesn't matter which one they're in. So there's only one way that you can do it.
There you go. There's only one way you can do
One way.
this.
Oh yeah.
Not n,
So it's like if you
but there's actually only one way to do this.
take as many groups as there are unique elements in a set.
As long as there's enough
I
buckets,
you're right. I said my answer wrong.
then there's only one way to do this. If you don't have enough buckets, there's no way to do this.
Your explanation was very good for it being.
Wrong answer, perfect explanation. So. And again, it's because we can't tell the difference between the buckets, so who cares which bucket the ball shows up in? Yeah, you won't be able to tell the difference. All the balls will end up in their own bucket. So we only have 5 minutes left. I had more of these bucket and ball questions for you.
He had more. There was none. Okay.
But I'll summarize.
I need
Let's
that.
summarize.
Hold on. Y'all, there's a picture of the table.
I think I put them all on your test review page if you want to look at the rest of them. But actually, this is the answer. I'm giving you the answer to all the bucket and balls questions we've asked so far, and more. What does injective mean? We talked about the word injective before. Injective means every bucket gets at most one ball. Surjective means that every bucket gets at least one ball. And what we're doing is we're counting functions, or we're counting mappings that map the set of balls to the set of buckets. And so over here, we can tell whether the N balls are distinct or indistinguishable, whether the R buckets are distinct or indistinguishable, and then whether the mapping is arbitrary, meaning you're allowed to have empty buckets, you're allowed to have, every ball in one bucket. Injective, which means you can't have more than one ball in a bucket, and then surjective, which means you can't have empty buckets. So the definition of Stirling number means no empty buckets, right? Blocks have to be non-empty sets. The definition of binomial coefficient is talking about an injective mapping of these things. That was the answer to one of our problems. And you can see where the rest of these fall in. You remember the one with a factorial and a Stirling number, and the one that was a sum of Stirling numbers and stuff. This is our running summary so far of combinatorics that we've learned in class together.